Like to see Lab City?
Well, yesterday I went from Ottawa to Lab City, and today I just came in.
Ottawa to Lab City.
Yeah.
That's a
You drove
long
all night.
drive.
Well, I left at midnight or something.
Yeah,
I got
okay.
at
He's a night
5,
driver.
so
He wants to get through that
As
Montreal
long as you
bit.
stay awake for the
Oh,
presentation.
yes, I can see that.
Yeah, without
But Montreal
traffic.
never sleeps.
All right, well, I think we'll get underway. I know most of you here know Robert, but we are recording for YouTube as well. We stream the talks on the YouTube channel as well, so people anywhere in Labrador can see them. So I'll give a little introduction here for Robert, and then we'll let him get on with his talk before he crashes for the night after driving in all the way from Ottawa. What, you left yesterday?
Yeah.
Yeah, so
wow.
yeah, lots of driving, yeah. So Robert's from Labrador here originally, from Goose Bay, right?
Yep.
Yeah. And he's done his, so you've got an undergrad degree from University of Ottawa, a master's from MUN.
Yep.
And now you're doing your PhD at back at University of Ottawa.
Yep.
Yep. Okay. The internet is right. So, and your talk is based on your master's research, or a bit of both?
Based on a little bit of everything. I started doing climate stuff in the end of my undergrad, and my master's was on glaciers in northern Labrador, so it was related a lot to climate stuff. And now I'm moving into frozen ground and permafrost in Labrador, so once again, climate tie-in. So it just kind of goes through.
Yeah, and that ties us into your title for tonight's talk, from glaciers to frozen ground, Labrador changing climate. So I'll hand it over to Robert and let him talk away.
Well, you can skip the first slide then, because I had a little introduction. But
Napkin time.
yeah, basically my undergrad, I started doing some work with climate, and master's was on glaciers, and that obviously involved climate again. And so now permafrost is my project, and it's a permafrost project, and we've been doing, I guess we've had 3, or is this 3 or 2? We've had 2 full field seasons in the summers here in Labrador doing work on that permafrost, and that's involved a lot of work, setting up weather stations, things of that nature, actually doing surveys of permafrost in Maine and things like that. If you could just, so I'm just going to give if you could just put the 3 up, I guess, a brief outline. I'm going to first start by just talking a bit about Labrador's changing climate and what the major controls are on climate in Labrador. I'm also going to then discuss the actual impacts that we see on some of the Earth systems, and also related a bit to do with human systems as well. So the first question is, why is climate important for Labradorians? Yeah, if you just, I think I've got 4 there, so just, 4 or 5 actually. So Labrador is important, obviously, because we traditionally use the land as Labradorians. People are very reliant on sea ice in particular, and also on lake ice to travel to subsistence areas, to get firewood, to hunt, and things like that. Snow conditions are therefore very important. If you all remember, in 2010, I believe it was, we had a very warm winter, or at least a spell of warmth in February, and almost all the snow disappeared that year, and it actually had huge impacts in coastal Labrador, where a lot of the areas like Nain and Makovic had a lot of trouble accessing traditional lands. Rain on snow events, it can be treacherous both for essentially on snowmobile, but also when it comes to hunting and things like that. There's actually issues associated with that, especially if you're on sea ice. And finally, warmer conditions actually can affect the animals that we hunt and the forests that we use. Last week there was a conference in Ottawa that I was presenting at, and I watched a few talks on that were quite interesting on caribou movements, and there's been some changes that have been observed that climate's playing a role, at least in where caribou in northern Labrador and in at least Quebec are traveling. So if you could go. So the first question that has to be asked is, what is climate? Weather, we know, is the day-to-day changes. Today's weather is -9, tomorrow might be -5. Climate is just simply summarizing the average weather. And it's typically done over long periods, like the average over 30 years, for instance. So in terms of climate for an individual location, a person, if you listen to the radio and you hear that announcer say that this is an above average spring, it means it's probably above average relative to the last 30 springs or something like that. So every individual year might be above an average or below an average, and that's climate. Climate is that average temperature, and deviations from that are anomalies, basically. So if we could continue. So continuing on, weather is largely controlled by systems. You have low pressure systems, high pressure systems, you have storms come in. That's weather systems. Now climate's controlled by different things. Of course, weather plays an influence as well. But when you average things out long enough, you start to see other patterns, like geographic position. So are you further north? Are you further south? Latitude and longitude, that plays a role. Elevation, areas higher up tend to be colder. They also tend to get more snowfall. Distance from the coast plays a big role as well. If you live on the coast, your summers are probably going to be cooler, as opposed to if you live inland, you might have warmer summers, but colder winters, for instance. And in that same regard, topography plays a role. So if you're in a mountainous valley, you might have more snowfall on one side than the other, things like that. This all plays a role. So if you could, so as we know, Labrador is a pretty diverse area, or the full Labrador GABA. The red line there depicts the position of the area tree line. So in Labrador, north of that area, the climate is too unsuitable for vegetation, or for at least full standing trees to grow. And also along the coastline of Labrador, you've got areas where trees can't grow, just because the climate conditions, the wind are too extreme. So if you can continue. Here's an example of the topography we have in Labrador. So this map shows elevation. The blue areas are areas that are essentially mountainous areas. We can see the Mealy Mountains, Red Wine, some of the ones in the southwestern corner of Labrador, and then of course the Torngat Mountains in the north. This next slide is going to be a picture of the Torngat Mountains. This is up in the northern Torngats where we were doing some work. You can see that it's above tree line, and that also you can see little masses of ice everywhere, and there's a small glacier that's located right in the basin of that top uppermost mountain there. Next one will be an example of the Mealy Mountains. This is just taken from the base of Kenemish. Once again, you can see that the upper parts where climate becomes unsuitable, there's no trees, so then you just see these barren grounds. The tundra really is once you get up to that height. And the next example will be same type of thing in the Red Wine Mountains. Once you get to certain elevations, the climate becomes unsuitable. You see little patches of snow. This was taken in, I believe, late June, so when we flew through at one point, same type of thing. You have above certain points, climate is a very strong controller on things like vegetation. So next slide, please. So when you look at the average temperature across large areas, another important role is the oceans. So if you could just do the next, yeah. So Labrador, we have cold Arctic water that descends in the Labrador Sea. And this is transported by the Labrador Current. So this is the reason, for instance, that we are much colder than places at a similar position on the Earth on the other side of the Atlantic. They have the Gulf Stream, which brings warm water up next to England. You know, Goose Bay is actually very similar latitude to central England, but yet we have a much colder climate than that area. And it's largely because we have this cold Arctic water that descends down across our coastline. So if you could just, next slide, just go through the whole, yeah, there you go. So that plays a role because we have seasonal sea ice cover, which reduces the impact of the oceans in the winter. So if you live in coastal Labrador, you could still have cold winters because you still have sea ice, which makes it a little bit more continental. The summer air temperatures along the coast also are very cold because you've had this seasonal cover over the ocean in that area all winter, and then you take it away and the water is still very cold, so that plays a role as well. And it also means that you have a big difference between the air above, so say the atmosphere, which is really warm, and the ocean, which is very cold in the summer, and that means you have a lot of coastal summer fog and low cloud and things like that. And that's also are all things that are common along coastal Labrador that people always recognize. This is a map that shows, if you just do the next slide, next thing as well. This is a map of trees. So basically, coastal Labrador, you see that they have cool summers and cold winters because they have very low temperature range. So that's the difference between the warmest temperature, the warmest monthly temperature, and the coldest monthly temperature. Whereas when you get into the interior of Labrador, say, actually that's more into Quebec and Nunavut, but you have very warm summers and you also have very cold winters. So there's a much greater temperature range there than there is in coastal Labrador. So for instance, anybody who spent time in Lab City, they have warmer summers than we have, and they also have colder winters by far. And so the further you go into Quebec, it gets even more extreme, the differences. And this plays a role on how we understand climate as well. So if we can continue. So if we put all these factors together, we can produce maps of air temperatures across large areas. This is a map of air temperatures across Labrador for the last decade from 2000 to 2009. And what you can see, if you just press the button again, is you can see the influence of topography. So you can see mountains that are cold in the areas around them. You can see the Torngat Mountains in the north, which is the coldest areas, the landscape across Labrador. All these patches of green in the south are all examples of areas that are high terrain, and so they're colder than the areas around. And you can also see that southeastern Labrador is pretty warm. Some of the average air temperatures in those areas are +2 degrees and things of that nature.
Robert, can you just remind me what mean means?
Average. So this is the average annual air temperature.
Yeah, okay.
So if you take every day in the year and average it together, and so usually it's considered to be a really important that this 0 degree kind of ice thing. This 0 degree annual air temperature is considered to be a really important thing. Sometimes it's used to demark the difference between subarctic and boreal and things like that. But generally speaking, for instance, if you have an annual air temperature above 0, you probably couldn't have anywhere formed glaciers. You couldn't have anywhere with frozen ground through the year, things like that. So that's the areas in red are roughly the areas that are above 0 degrees, and the areas in, say, darkest blue, the coldest areas in the landscape are about -7, -8, which is very cold. That's actually similar to areas in the Arctic, which is kind of interesting. If we go to the next slide. So one of the things that's really important about Labrador's climate is that it is very variable through time. So these are two maps that are once again the average air temperature. One which is showing, they're on the same scale, surprisingly enough. One on the right showing what happens in the warmest year, and one showing the coldest year. And what you'll notice is that in the warmest year in Labrador, the coldest single spot in Labrador is the same as roughly amongst the warmest spots in the coldest year. And in the warmest year, you see none of that dark blue color. You see none of even the second darkest blue. And just like in the coldest year, you see none of those. You see nowhere that's above 0. So our climate is very variable in an individual year, and that actually has a huge impact on people. So if we could just continue to the next slide. So this is where climate change comes in. So when people talk about climate change, we know that our climate changes naturally a lot. But people are talking about human-caused climate change when they bring up climate change. This is known as global warming. It's in essence caused by an increase in these particles in the atmosphere that trap heat. They slow the escape of heat to space, and most of this heat stays actually goes down into the oceans, but a fair amount of it stays in the atmosphere. And so that's what they talk about when they talk about global warming. They talk about this percentage that stays in the atmosphere and warms. So if we can get to the next one. So some of the interesting things about climate change is it's supposed to occur fastest in the winter months. It's supposed to be more noticeable in the night than in the daytime. And there's this talk of what they call feedbacks. And isn't that, in essence, something where you have an initial change, say the atmosphere is warming, and because of that change, something happens. Either it amplifies it or it acts the opposite. So an example would be if you have, say, warming in the winter time, that melts snow and ice. which in turn exposes darker ground or water around. And that darker surface absorbs more heat. So when you think of snow sitting there and reflecting all that sunlight as opposed to a dark ground surface, it makes a big difference in terms of the actual air temperatures and things like that. It's called a positive feedback in this case. So if we continue. So if you take a climate model the climatologists use and you run it for, let's say, the last 30 years, this is in this case, or not exactly the last. Could you do the next slide? So yeah, the color didn't show up terribly great, but what it in essence shown is that for the winter time, the prediction was that you would have a warming of about 0.5 degree in the northernmost areas of Labrador, and in the southernmost about 0.3 degree, but that as you went further south, there would actually be no detectable difference in winter temperatures. So if you can go back to the previous slide. So as you notice, there's some parts of the world, such as most of the United States, which were expected to have no impact of climate change over the last 30 years. And then other areas in the northern areas, which were supposed to, some areas having, up to 1 degree centigrade increase in winter temperatures. If we can go to the next slide there. Whereas in the summer, it's uniform. You don't have these red spots on this map anywhere. And Labrador in general is expected to warm about 0.3 degree in the summertime, which is less than in the wintertime. So this is just an example of what they show you when they produce climate models for an area. So this is the general trend in Labrador air temperatures since about 1880, when the first temperatures were being taken by, say, Moravian missionaries in some of the coastal areas. And as you can see, if you just do it once, there's a long-term trend, actually twice, a long-term trend of warming, which is about 2 degrees Celsius. So overall, in the last 120 years, 130 years, the climate has warmed by about 2 degrees. But what's also noticeable, if you can do it again, is that over the last 20 years or 30 years, that exact 2 degrees has happened as well. Because previously there were warm periods and cold periods, but there's been a very quick warming over the past 30 years. And in particular, that has raised temperatures by 2 degrees. And it's occurred much faster than the overall trend if you look at the full period. So here's an example of 2 maps of Labrador, the air temperatures that would have been estimated for a century ago versus compared to now. And what you notice, for instance, is that if you can just do first line, the Red Wine Mountains in central Labrador a century ago are the same as what northern Labrador is now. And the next example will be for Nain. The conditions that were expected in Nain for now are about the same as what were expected for Rigolet a century ago. So this puts a bit of a face on things. So going forward, that's kind of an interesting way to look at it, is looking at it in terms of how is your local climate going to change to be more like maybe in other cities. But so Nain, the way we think of the conditions now, that's exactly how people would have thought of it at that point in Rigolet. And that also plays a role when it comes to understanding human migration as well. And when people look at, say, the distribution of Inuit along the coastline in Labrador, that's changed in turn with the climate over the past few centuries. So if we can go to the next one. So one thing that also sticks with this map, and then the next, is that you have some years that are really extreme. These are years where temperatures have been either really cold or really warm. Now, there's 2 of them, and if you can do it again, which are these large drops that happen at the same time as volcanic eruptions. So what happens when a volcanic explosion occurs, it puts all this dust up in the atmosphere, and this dust then reflects sunlight. And so it means summers are really cool, especially in high latitudes, just because of atmospheric circulation hauls all this dust up there, reflects sunlight. So in Labrador, we have a really clear response in those 2 years in particular, where there was these huge, massive volcanic eruptions, and as a result, our temperatures went way down. The next one is an example of there was a burst of cold water which came from the Arctic and went right into the Labrador Sea, and it only did it for actually 1 year. And so basically this bubble of cold water came down to the Labrador Sea, and you see the coldest year on record, just because essentially a little mass of water moved over. So what that says to us is that Labrador's climate is very sensitive to what goes on around it. And the final example is 2010. The 2010 year was the year that had average winter temperatures of about 10 degrees above normal through December, January, and February. And although there's an impact of climate change on that, unusual conditions that were going on in the atmosphere at the time also played a large role as well. So you can't tie this individual event to something like climate change, because there were other reasons which drove that warming. So we actually, when we were doing this project, and you don't have to understand it all what's on this, it's a ton of things, but we were doing this project and we ended up publishing a paper. And what we did was we looked at Labrador's climate through time, and we tried to understand what caused the year-to-year changes. And all the things that are lining up here are just simply different atmospheric events or volcanic eruptions, different phases of different things. But in essence, by doing this, we were able to build a model. And if you do the next slide. And so if this is the observed air temperature through time, we built a model, which guessed what the natural factors that contributed to climate change in Labrador were. So this model shows basically what natural conditions, just weather in essence, was doing in year to years. And what you see is that in the last decade in particular, it seems a lot lower. So what we did then was we tried running the same model, but we tried adding in human influence, so anthropogenic causes or human-caused climate change that we got from a climate model. And what you see is a really good fit. So that says to us, in particular, next slide, that the difference between global warming and, let's say, just year-to-year weather has only been able to be detected over the last 10 years, or maybe 15, something of that nature. So that before that time, you wouldn't be able to tell that climate change was anything different than just naturally occurring climate change. But certainly over the last 15 years, we can see a clear difference where temperatures are warming. So even at the local scale of an area like Labrador, we can tell the difference in our climate conditions just based on this work that we've done. And so the next slide. So based on this, we figured out some numbers and said that about 65% of the warming since 1995 was caused by global warming in essence. And that the remaining 35% was related to some seasonal weather patterns and natural factors. So what this means is that some of these years that I spoke about, like 2010, they did have a contribution from climate change, but that seasonal weather patterns play a role as well. So this makes me think that, if you can go to the next one, that 2010 is a better example of maybe what the future will hold, rather than calling it climate change today. This graph is a bit hard to understand, but basically those black dots are individual months what the temperature difference was in 2010. The blue line there with all the different dots is what the temperature change was over the past decade. And the red lines with the dots is what climate models predict for 50 or 40 years from now. So basically, the black dots, when it's within the red lines, it means that it's pretty close, it's at least within the range of what climate models predict for 50 years from now. So what you see is that for January, it's within that range. For February, it's actually above. So February was warmer than what climate models predict Labrador's climate will be like 50 or 40 years from now. March was on par, April was on par. The May, June, July was a cooler period, and once again, then you get a series of months that are on par, or once again, December was above average. So what this says is that 2010, maybe the summers are expected to be a bit warmer than 2010 was, but the winter months, pretty similar to what the conditions will be then. So when people think of how difficult the snow and ice conditions were in 2010 that year, where there was water everywhere, where people couldn't access these lands, this gives us an idea of what you would expect to be the case, say, 40 years from now. So next slide. So this is in essence what climate models predict. The red line being if the world stays going on a very high emission scenario, which it seems to be at the moment, and the yellow being if we have high emissions for a little while and then we taper off, we actually do something about climate change. So 2010, you can see that huge blip, pretty close to what you're expecting for 2055 or something of that nature. What's pretty evident from this graph is that potentially by 2100, it's pretty huge changes. But also that there's a big difference between if there's something done with respect to climate change and if there's not. So if they just continue business as usual, you're going to have a lot different conditions 50 years from now, as opposed to if there is no action. Can you do the next slide? So, for instance, that 50-year point, the temperature today in Quebec City, say throughout the year, is similar to what conditions will be like in Goose Bay 40 years from now, regardless of, say, under the high emissions scenario at least. And it'll be similar to 2100 under the low emissions scenario. So whatever the climate is like today in Quebec City, that's at least similar in terms of air temperature to what we would project for 40 years from now for Labrador if things continue the way they are. And unfortunately, one way or another, there's a certain degree of, because we've done the emissions the way we have right now, there's a certain degree of warming that's going to happen anyways. So whether that should be something, whether it will reach all the way to those levels by 2050, even if we stop emissions now or not, I can't answer. But what I can say is that's what you're looking at. Now, if things continued all the way to 2100, then Goose Bay's temperatures would be like Toronto. So that's quite an extreme difference. That would imply that there was no change at all in emissions. So the hope is, at least anybody who's been to Toronto versus being in Quebec City, that at least it would be better to go on a medium emission scenario as opposed to a high range scenario, because Quebec City, at least we still have a winter, but either way. So yeah, the difference is quite big. And so if with this graph here, we see this is the estimated air temperature for the first decade of the 1900s. And this is on the right is the estimate for the middle of the century, the point I've been using all this time. And one thing you'll notice, do I have arrows in that? No, I don't actually. Okay. Well, one thing you'll notice is that, say 100 years ago, when this first graph is taken, or this first image is taken from, you have huge areas of this green color, which is about -3 average air temperature. By the mid-century, that's about 500 kilometers further north. So when you think of all the different vegetation changes that are related to a warming climate, you think of animal ranges, when you shift essentially biomes 500 kilometers north, that's a rather significant change. It also, when you look at this map and you look at the areas that are above 2 degrees Celsius, all the red, you're changing a huge part of Labrador in a very short period of time. 150 years to go from essentially the climate on the left to the climate on the right is rather quick. Just continue the next one. So one thing that we've noticed, and I'm sure people who spend a lot of time on the land have noticed, is that there's been very rapid growth of vegetation in the tundra. This is an image from the Torngat Mountains. Obviously, the Torngats are far above tree line, but there's an awful lot of more shrubbery now than there was even 20 years ago. And another big difference, and this is actually playing a role for elders and people who hunt on the land, is they're finding it a bit more difficult to work in the Torngads or to hunt in the Torngads because there's more, you have to be more aware of bears because obviously with much higher shrubbery, you can be walking somewhere and not know that there's something in the woods there. And certainly plays a big role with black bears, which up there are more carnivorous, but polar bears as well. And that's something that in particular when you get to the lower elevations, it's more of a role there. But we've seen the same types of things through other areas in Labrador that you have this expansion of willows and shrubbery and all this kind of stuff in spots where it wasn't before. So next, is it? Yeah, so the next part I was going to discuss a bit was changes in glaciers and permafrost, which is where my work also continued. And yes, we do have both in Labrador. This is an example of some glaciers. Sorry, it's in black and white, but you can see the white parts. Our glaciers, actually the C is an area we worked in. Actually, no, we worked in A and C, and both in the southern Torngat Mountains. And these glaciers are mountain glaciers. They're in this kind of steep topography that keeps them pretty shadowed, so they don't get a whole lot of solar radiation. They don't melt a lot, but they don't really accumulate a lot either. So if you go to the next slide, just next to. So just a quick review. Glaciers are, in essence, they're these big bodies of ice, and they accumulate to a certain thickness, and then they start to flow. So they actually move, and the glaciers in Labrador probably don't move very quickly, but some of the ones in Greenland move multiple kilometers per year, things like that. So this weight just lets them move down slope. And in Labrador, we have very small glaciers. They're all less than about 100 meters thick, and the longest one is about 1 kilometer long. So they're very small, and small glaciers are thought to be very sensitive to climate change. So if you just go to the next, we did an inventory of all the glaciers in Labrador. This was the first one that was done, and there's about 195 that technically are called glaciers. Only about 105 of them are large enough and to be actually flowing so that you can see these crevices and that they actually look like glaciers. But in general, what's interesting about Labrador is they are even very low in the mountains. The second you get into the Torngat, you can see ice in lots of locations that are very low, which is very interesting. And the largest one is about, in full area, it's about 1.25 kilometers, which I believe I'm trying to remember what I made a comparison to before, but I think it's about 80 times the size of the soccer fields up on base, which is small relative to other areas, but when you imagine being on a feature that big, it looks pretty big at that point. But most are pretty small. If you can go to the next. So this is an example of photographs taken at the terminus of the glacier in the northern Torngats. First one's from 1906, and you can see this front of the glacier down, almost approaching that small little lake there. The second one was taken about 25 years later. You can't really see the end of the glacier, but you can see the ice behind it. And the third is from 2008, and all you can see is the remnants of ice in the back. And that glacier has actually separated now into 2 glaciers. So you actually have one piece of ice there and one piece of ice there, which is a pretty big change for that individual one at least. So as part of trying to understand how the climate's changing, it's useful to look at glaciers and things like that. So what we tried to do as part of my master's is we tried to look at how glaciers were changing from a period known as the Little Ice Age, which in essence is a couple hundred years ago. It's the last big cold period, to present. And so when we did that, if you can go, we were able to map where glaciers used to be for about 160 glaciers. And in essence, most of them have lost a fair bit of ice. They've actually decreased in size by about half on average. But the thickness, they're definitely a lot thinner as well. But that's something that's hard to be able to tell. You go into the field and you can get ideas that this one's probably way thinner than it used to be, but you can't, it's very difficult to quantify it. But like we said, they've declined by about half over that period, which is a couple hundred years. But if you go to the next slide, this is just in essence a map of the Torngat's. It shows the topography, so you can kind of see the mountainous terrain. And glacier change is just reflected in the dots. So the red dots are examples of glaciers that have nearly completely disappeared, and the green little tiny blue dots actually and the little green dots show less change. But what you see is that there are some glaciers that are disappearing. We actually noted 8 that completely disappeared and a lot that actually declined by over 75%. So they're just holding on by they're just holding on by their bones basically. So if you can continue to the next slide. So then we looked also at recent changes, and we did this over a very short period, a 3-year period from 2005 to, and you don't have to read the whole text there, but in essence what we found was that about 9% of the total area of the whole glacier range was lost in those 3 years. And so over those 3 years, 91% of all the glaciers that we looked at, so about 88 or 87 glaciers had shown decline, and overall it averaged about 9%, which in 3 years is pretty quick. And we haven't actually been able to complete another inventory since then, but we're going to at some point. But at least from field observations, it's happening fairly quick that they're declining, at least some of them are. If you continue. So I'm now working on permafrost, which is another kind of Earth system that is strongly related to climate. And permafrost is, the actual definition is, it's ground which remains below zero for 2 consecutive years, but most people know of it as frozen ground. It's actually, there's a little difference, one being a temperature thing and the other, frozen ground actually means that there's ice in it. So that's actually what makes it important when it comes for development and infrastructure, because if there's ice in this frozen ground, in essence, ice expands the size of the surface. So if you take away that ice, then you get subsidence. You basically get that. An example of it, actually I'll show an example later, now that I think of it, but that's why it's important. It's really expensive when you have issues with permafrost. Even seasonal frost can be an issue. In Maine, for instance, there's been some recent work that's found that about 80% of the houses in Maine have their foundations cracked because of either, heaving during seasonal frost or permafrost related issues, and it's very serious. And in other parts of Canada, there's been a lot more permafrost work done, mainly because they built either industry or they built roads through particular areas that had a lot of it. And in particular, the Alaskan Highway, when they built that, they spent millions and millions and millions of dollars on permafrost issues because the road kept collapsing. In northwestern Quebec, so let's say in Nunavik, they have a lot of permafrost there, and so they've been working on that for many years. If you can go to the next slide. So in Labrador, as part of the work we've been doing, we've been trying to map permafrost, and it's very isolated patches you get in the southern areas, but as you go further north, you encounter more and more. The dark blue dots are spots where we're currently monitoring bodies of permafrost. The light blue are ones we know exist, but we haven't done monitoring on yet. So when I say monitoring, we have set up climate stations there, we've done measurements, we've taken ground temperatures. We're trying to understand how susceptible these areas are to change. So what you'll notice, even as far south as Red Bay and Blanc-Sablon, the southwest corner, southeast corner, has some bodies of permafrost. When you get to the southern end, you get these features called pulses, which are shown in this example here. This is one in Cartwright. What you'll notice is that people have been storing their comatics on top of them, because in essence they remain fairly wind-blown during the winter, so you can easily hook on and access your comatic there. And that's also the main reason why they form, because they don't have insulating snow cover. Basically, you have a bog or a marshland, and it has, for whatever reason, a particular part of it might not accumulate as much snow. So let's say the ground gets cold, and eventually it heaves up, and you've got an ice builds up underneath and things like that, until you have these surfaces like this one, which probably remains fairly bare during the winter time because the wind blows all the snow off. And these are found in a lot of areas of coastal Labrador, and they can also change fairly quickly. So they're not necessarily important from an infrastructure perspective, but they're definitely features on the landscape that are noticeable that can change. And a lot of people actually have identified these types of features out berry picking because, when you go, actually even when we visit some of the sites in southeastern Labrador, we were doing work, but there were bake apples all around. So we might have picked a few, but anyways, especially, I've actually spoken to a lot of people who have noticed these types of features when they're out berry picking and things like that. I will say that the flies are horrible when you're doing work in bogs, so I wouldn't suggest spending too much time around them, but next slide. So this image, it's really complicated, but it's basically, we took up a set of equipment and it lets us see into the ground. So this axis here is the depth into the ground. So this is 26 meters, it's the deepest part. All I want to show is that there are several bodies of permafrost, with the deepest one, this is our limit, so the deepest one being about 18 meters deep. And this is underneath where they're actually building the Tungatsu Cultural Center in Maine. So they've actually had to, they drilled some boreholes when they were actually doing the plans for it, and they encountered permafrost. And when we were up doing work in conjunction with the United States government, we decided to do a survey across there just to see what our imagery or our system could see in the ground. And we could pick, permafrost. The presence of permafrost there doesn't necessarily mean that it's going to be an issue going forward as long as they deal with it. And I believe in the engineering for that building, they have tried to put piles down, which is a way of dealing with it. And at this point, it's unknown of how the permafrost of this site will react, but at least it was known going in. So that's the difference today if you're doing a project like this versus maybe 50 years ago when you would just build something somewhere and you wouldn't necessarily know what's underneath. So here's an example of the next photo of what happens when you build somewhere without knowing there's permafrost underneath. This is Puffin Snacks in Maine. And what happened was, in essence, the permafrost thawed beneath the structure there, because when you put a structure over a body of permafrost, it usually warms the ground by about 1 degree. And in a lot of cases, if there's ice in the ground, it means that that ice melts and the ground compacts or subsides. And so this is an example of that happening there. This is actually, ironically enough, if you can see the truck on the right side there, that's close to where the cultural center will be built. So it seems to be that there's an entire string of basically houses and buildings in a row that all have issues with probably permafrost, but throughout the community there doesn't seem to be a huge permafrost issue, but at least in that area it seems to be more of one. And we actually went up to upslope from there and did some surveys in a site just a bit further up that was forested and not touched, and we found permafrost there. So it probably just means that that particular area of town just has an issue with that. The hope is that there is no issues with building the cultural center, and presumably the engineering has dealt with that. But this is a real impact, and we don't know yet if any other communities have permafrost related issues, but it's certainly something that's to be considered when it comes to building roads. I know there's been talk of building a road from Northwest River to, for instance, Postville, I guess it would be. You're not expected to encounter a whole lot of permafrost along there, but these are things that have to be considered. I know they did have some issues when they initially built, for instance, the rail going from Settile to Shefferville. They had some areas they had to compensate for, come in and put in more fill and stuff like that. They also had huge issues in Shefferville when they were mining there with permafrost, because apparently permafrost, when you're mining it, you have to blow it apart first. So they had to use all kinds of explosives to blow it up. They also encountered it in Lab City when they were doing some mining as well. And actually Twin Falls, before they built Churchill Falls, they had Twin Falls, which was actually used to power, I guess, mining operations in Lab City, and then they diverted the water towards the actual big structure. But they actually built their entire structure in Twin Falls on a site that had all kinds of permafrost. They had to excavate out the whole valley and all that kind of stuff. Probably cost a lot of money. So it's just, in essence, saying that it's something that has to be considered with future development, depending on where you live. So finally, I just wanted to end off with discussing a little bit what, in essence, does climate change mean for Labradorians? It means that we should expect some warmer winters. It means that the ice conditions may become less predictable. You might have increasing vegetation cover, more shrubbery in certain areas. Animal migration patterns will inevitably change, especially if you change ice conditions. I mean, when you think of a migratory herd, like the George River Caribou herd, this herd uses ice very frequently to travel across large areas. So if there's less of a pathway, maybe they take a different route, things like that. More mosquitoes, which is an unfortunate circumstance. If you warm up the summers, if you warm up the winters, if you warm up the springs, you have more mosquitoes. So it's expected that mosquitoes will increase. Interestingly enough, my first season up in the Torngat Mountains, people were shocked at how many mosquitoes there were, because I guess 10 years prior, there hadn't been many. And I can remember being on top of the mountain in the Torngats, one of the highest mountains, standing on a glacier, and there were mosquitoes flying all around my head, which is kind of a weird thing. Another thing with the warmer summers is that caribou actually use a lot of these snow patches that you find in the upland areas of Labrador to escape as shelters from mosquitoes and bugs and things like that. And they are seemingly disappearing, so that obviously plays a little bit of a role in where they want to go. Finally, we talk about thawing permafrost and melting glaciers. Now, for thawing permafrost, yeah, there's the potential it has some impacts on some people. Melting glaciers are more of a cultural entity, because there's not a whole lot of people who really have much to do with them. In other areas, like say in the Himalayas, if you melt glaciers, most of the water that people get downstream is from glaciers. Whereas in Labrador, hydrological changes aren't probably a major concern for most people, but they are a cultural entity. They are something on the landscape that's disappearing, and that has value. And they're also the southernmost glaciers that are in the true Arctic. So these are, in essence, bellwethers. They're the limit of where you can get glaciers in the Arctic. And with them expected to at least decrease over the next century, it'll be interesting to see how many remain, because we're seeing fairly rapid changes. One thing that I was certainly wanting to bring up before I switch slides, with ice conditions being less predictable, and we know, as I was showing earlier, roughly how climate is going to change over the next 40 years, there certainly has to be consideration for how we deal with this. I imagine that in the winter of certainly a lot more people using overland routes rather than land ice and sea ice routes, because a lot of people went through the ice those years. So if you can go to the next slide. So kind of to summarize what's been said and to describe a bit climate change in Labrador. One thing that I noted, and I tried to note early on, is that Labrador's climate, although we are seeing climate change, it's a climate that's very volatile. You have very big year-to-year variability. So it's not surprising that Labrador's climate is characterized by periods that are very quick warming, and then you have slow warming, or that's what we would expect. Because at some points, the weather is going to be working against climate change, and on some points, it's going to be working with it. So over the last 15 years, I said 65% was probably around what was due to climate change. The other part was weather. Well, So that other 35% contributed to warming, so that's why it warmed faster than we would have thought it would. So in the same context, maybe next decade that 35% will act to cool, and so maybe it won't warm as quickly as it has the last 15 years. It's about being prepared for these periods and this volatility that you could have 10 years where maybe you don't have as much warming, and then 10 where it warms really quickly and we're not prepared. So we have to consider the way we change our lifestyles and how adapting to a changing climate can be done. I know that there's a lot of work that's being looked into on these subjects by other groups as well. And it really has to be something that does have to be considered, because Labradorians are in essence very reliant on our environment around us. And certainly when it comes to our winter travel, we have to find alternative means of getting around without having to be depending on ice conditions that can be very variable. And in essence, preparing for the unexpected is what I hope that we're able to do. 2010 came and it seemed to hit everybody like a truck. There will be more years like 2010. So it's best to be prepared in advance rather than to wait till it happens and we have somebody, for instance, go through the ice and pass away or something of that nature. Thanks.
Questions for Robert? I'm going to ask you one. How about, you didn't talk specifically about precipitation, but I think that was one of the findings from the John Jacobs research in the Mealy Mountains, that there was supposed to be increased precipitation for Labrador in the coming years as well.
So what's expected, I didn't talk about precipitation because in essence it's very difficult to, precipitation is very volatile. Year to year, there's way bigger changes than in temperatures, and it's also very difficult to separate what is caused by, let's say, human activity versus what isn't. The climate models still aren't, I'm not going to say up to par, but I'm just going to say that modeling precipitation patterns is very difficult. It is expected that precipitation should increase in a warm climate. That's because warmer atmosphere is able to hold more moisture. So you should expect precipitation to increase. The spatial patterns of how that happens and the patterns throughout the year are something I probably couldn't speak to, but what I can say is that having an increase in precipitation doesn't necessarily mean an increase in snowfall. It could mean you have more rain on snow events. It could mean that you have more precipitation in the shoulder seasons. We expect that snow cover is going to decline. Whether that we have more rain at the end of the seasons or something of that nature is something that is still yet unresolved, but it is expected that you'll have more precipitation and you'll have more intense precipitation. So there is the potential to have more storms, but those are all issues where things are yet undetermined fully.
So how can you explain a big change like right now, like today? I don't know what the temperature is outside, but we'll say
-8 or something.
-8 or something like this. And yet 40 years ago, it was around -65 Fahrenheit.
So
Why the big?
there's obviously the difference between weather and climate. I mean, any individual day, you know, you'll even hear when you listen to the radio, there's a daily minimum, a daily maximum. You know, some days are at their maximum, some days are at their minimum. You should see with the warming that's occurred, less minimums being hit. Doesn't mean you're not going to have years where your minimums are hit. Look at last Christmas. You had some days at Christmas which were the coldest in 40 years, but you're expecting to break cold records less frequently than you're going to break warm records. Records broken. The other thing, and one thing that I didn't say at the start, but that I should, and this is a question commonly that people ask, is with weather forecasters, if it's very difficult to project what the weather is, say 5 days from now, how can you project what it's going to be with the climate in the future? And one thing we're thinking about is a climatologist, for instance, will be able to tell you, well, okay, I can't predict what the temperature will be on April 15th, 2050, but I can tell you that the spring is going to be warmer than the winter because things follow natural laws. I can tell you that winters will be warmer. Can I say that there will be no days that are minus 50? Probably not, because I don't know what the day-to-day weather is. But I can say that there's going to be less of a chance of encountering those types of days. I was going to put it together, but I didn't have enough time. A graph that's showing the number of days above certain temperatures or below certain temperatures through time. But what you can see is that certainly in some areas in Labrador, your chances of encountering days of minus 40 are a lot less than it used to be. But you can still have them. It could still be next week, could still be minus 55. But it's just going to happen less frequently.
Yeah, that's why it's important to explain that difference between weather and climate, right? Because a lot of people who would use common sense arguments against climate change are basing the perception on their experience of weather over from a year to year, like a day-to-day basis over a number of years, as opposed to being able to anecdotally relate changes to climate, because your body's not going to necessarily, your perception's not necessarily going to register 1 degree climate change over a 10-year period when you've been experiencing peaks and lows and weather over that time.
Well, I find it's a bit easier here than other spots. Like when I go to, when I spend my time in Ottawa or wherever else, and you say, okay, climate's going to warm a degree or two, they say, well, that doesn't mean a whole lot. But so for people in Labrador, climate's warmed by about 2 degrees over the last 25 years, and you ask any elders and they notice. I mean, it's pretty clear actually, especially in the winters. So it's all a frame. It's called your frame of reference. Let's say for people who are more connected to the land, there's these changes actually mean more. Let's say than if you're not really using the land in the same way. But that is a common argument. In a single day, you have daily temperatures which range so much and change so much. So how can 3 degrees matter or something of that nature? But it can make a big difference. And certainly when I showed some of those maps, I showed the areas that are above 2 degrees Celsius increase a huge amount. Well, for permafrost work, you shouldn't have permafrost anywhere that's above 0. So you're taking a huge chunk of land that will no longer have frozen ground, or at least perennially frozen. And that actually has a big impact on hydrology, surprisingly, because you have this big mass of ground that water can't penetrate through, so it's over. Well, if you take that away, it completely changes how drainage occurs. And so in areas around Nain, for instance, there have been some lakes that have disappeared because they've drained. There's been permafrost underneath, permafrost disappears, the lake drains. So you could expect there to be at least changes at the landscape level as well.
Well, you talked about human activity affecting climate.
Yep.
And I mean, I would think that most of the human activity that affects our climate has been outside of Labrador.
Yeah.
But
So
then, I mean, I just was thinking, like, what are some of the major human activities in Labrador? Well, the creation of the Smallwood Reservoir.
Yep.
And maybe the mining in
So-
Lab West. Like, what activities, or are there activities in Labrador that are affecting climate?
undoubtedly, at the local scale, there are. Like when the Smallwood Reservoir was produced, that definitely impacted the climate of the area. You put in an inland sea, in essence, where there used to be land, and that certainly affected things. But when I say human activity, I mean that, in essence, in the industrialized countries, and China in particular, and the U.S., they're burning a lot of coal in particular, and the carbon dioxide from this coal goes up in the atmosphere, circulation takes it around, and the largest impacts are in the Arctic. So ironically enough, the people who are going to be most impacted are the people who have the least actual influence. And it's actually very clear, it's become much more clear that this is going to be an issue. And certainly the further north you go, actually, the greater impact is expected. So if we're expecting temperatures to increase by 3 degrees, let's say, or what? Yeah, I guess 3 degrees by 2050, or by 2100, they're expecting 7 degrees warmer on Ellesmere. So certainly the impacts in those areas are going to be huge, and it is a certain sense of irony that what's going on in other areas affects the high latitude areas the most. But that's one of the reasons why I think there's such a difficulty in finding action on an issue like climate change, because when it was the ozone hole talk, well, people acted, they got together, they did the Montreal Protocol and reduced the use of CFCs was the culprit. That was, I guess, used in fridges and stuff. And so that was destroying the ozone hole. What happens is when you destroy the ozone hole, you get more incoming radiation, and that was affecting everywhere. So people were like, gee, that could affect me. We need to do this. But when its impacts are mostly felt by very few people in northern areas, then there's less of an impact. Or when it's, for instance, a lot of the people who will be impacted by climate change are people in Africa or people in India. So far away from where a lot of the greatest sources will be, because the unfortunate thing with climate change is a lot of the areas that are the wettest are going to get wetter, and a lot of the areas that are the driest are going to get drier. So droughts will be larger in some of those areas.
So that in turn might lead to people who live in the dry areas start trying to start wars and that
Oh, there'll be huge migration
to get areas where there's more moisture.
Well, I would say that stuff has even ongoing throughout human history. I mean, you know, it's only let's say the last 100 years and stuff that people have spent more time staying in individual locations. Let's say, well, not maybe 100 years, but longer. So one thing that I think of very often is when you think of what happened in New Orleans. That's a city that's built below sea level, or chunks of it are. It was struck by a hurricane about 30 years ago, and they had a lot of issues with flooding, and they swore they will, rebuild, and if it happens again, they'll rebuild bigger. And so when you build a city on the coastline below sea level, and sea levels are rising, which they are, then you will constantly be fighting this battle. And we've decided that some of these coastal areas are where we want to live, and it just means it's a bit more expensive and also costly of lives if you have as much sea level rise as is expected.
Yeah, Glenn Dyer's argued that, and whether you agree with him or not, that the next driver of war in the world will be climate within the next 100 years.
Yeah, I read that.
Just like your point that all these countries that people can no longer live in most of them have some of the largest populations in the world. So they're going to have to migrate to other locations. Even the southern United States, the agricultural belt in the southern U.S. already suffering from droughts now. It's going to get worse. Some of those people are going to have to probably relocate to other locations as well.
Well, I know that there was a study that came out this week that said that California is going through, or just finished going through, the biggest drought in over 1,000 years, which obviously has huge impacts for the people there and also for us who eat fruit from there.
And avocados, I read it before I came. Someone said, what's going to happen to your avocado toast? And I don't know, what? And so I hurried up and read, and they said, well, because it's developed in areas that take a lot of moisture, in like California, they're one of the main producers. And because of these droughts, there's just an actual shortage at the very time that they're becoming like more and more popular in guacamole and all that kind of stuff. And so suddenly, just as you've learned to love them, they're actually going to be harder to get or more expensive or whatever. So it's, and you see immigration too in our country. I mean, immigration is always on the news now, and issues and backlogs of 10,000s. And so already you see cutting edges of people trying to get to countries that are more hospitable in terms of like droughts and things like that. We don't have those things. They want to get away from the tsunamis and the tornadoes and the horrible features of some of these climate things, right?
Well, one thing is it's not all doom and gloom. I mean, growing seasons are going to increase in Labrador, for instance. So we don't have the greatest soils for growing. That's our main limiting factor here at Goose Bay. But maybe there will be more potential for certain things. I mean, there may even be some changes in the species of animals that we get here because the conditions are more favorable for certain types. Overall, I mean, in Labrador, the largest impacts are going to be felt by people in coastal New Nazi, really, because they don't have road access. They don't have alternative means of getting in some of these supplies. And that's quite a pity because, it's very difficult as is to get there, and then you it's not necessarily going to take away, but you make conditions less predictable. Ultimately, that's something that I think people are working hard to try and rectify, and I think that going forward, it's something that should be, to some degree, there should be more of a government push towards monitoring these types of things as well.
Rather than just television commercials?
Yeah. Yeah. Either way, it's our work. I mean, I'm still continuing with this type of work for a long time, and I've got a couple of years left of my PhD. It's going to be a lot of permafrost related stuff, but that always links to climate, and the hope is from all this work that we're able to better inform some practices within communities, in terms of where to build, where not to build, if you want to avoid frozen ground as being an issue. I know that Nain is probably the major community where that would be an issue, because it's one of the only ones that we've encountered permafrost, at least near houses. I know in Wriggle and Cartwright and Red Bay, there's permafrost, but it's only in the bogs around the community.
Yeah, it may be becoming an issue in Shashi, where they're starting to build houses on the edge of the bogs. We dug test pits this summer for archaeological purposes, but that was in August, and the ground was frozen. That was this much moss on top, but then below that is frozen solid. Yeah,
I mean, it could be permafrost, it could be seasonal frost as well. We encountered a lot of seasonal frost in bogs as well, and it will stay until...
Especially after last winter.
Well, yeah, last winter in particular. I mean, there wasn't much snow, so it was very cold, but in reality, Labrador has way less permafrost than it should for the air temperature it is. If this were in the Yukon, the conditions we'd have permafrost most everywhere. The reason we don't is because we have so much snow. So it basically keeps the air from getting to the ground. Most of the sites I go to, and we've put down loggers in the ground at about 40 sites, most of the sites at normal spots, the temperature at the ground, in the ground, doesn't get below zero, most spots. So none of the frost, even though last year was minus 58, none of that got to the ground in some spots because the snow is so thick. But it also means in spots where it's windblown, you almost certainly have permafrost, or you have a good chance of it. And so I really should have shown some pictures, but in some of these areas it's really interesting because you get to the tops of mountains, for instance, which are windblown, and you can see all these circles in the ground that are sorted and things like that, all these the frost action, basically. So you can tell there that there probably is permafrost because Clearly it was snow blown or something. But in most areas, yeah, I mean, Lab City should have permafrost based on its temperature, but it doesn't because it's got so much snow. There probably isn't some areas, but you know.
Yeah, I've never had, I've done lots of test pits over there too, and had photos down at the end of June, but
Yeah.
never in July or
Yeah.
late July or August.
What I found interesting was that basically they've said in the past 15 years, we've had 10 of our warmest years in the past 15 years. So obviously there's something to make that many warm years in such a short time. And yet at the same time, last winter was actually one of the coldest for a long, long time. I know even here in Goose Bay, they've only had records for 77 years, but in the month of March last year, it was the first time in all of those 77 years of records that not one day in March went above zero. And that never had happened since they've done records. So in the midst of all that warming, then you had this anomaly, like a really, really cold winter. That
This summer was actually really warm. When I look at the records, summer was about almost 3 degrees above normal. So the winter was about 4 or 5 degrees below normal. The summer is 3 degrees above.
so how it's slowed.
This year is actually going to be not a cold year per se when I average it all out, but it'll be above average, but not by much. It won't be like 2010 was 4 degrees above average. This year might be half a degree above average. So one thing that I didn't show, but that's kind of interesting, is there's expected to be the potential that maybe the warming that we've seen will slow down for a bit, maybe even 10 years or something of that nature, because of what's going on in the Atlantic Ocean at the moment. There's just a natural cycle that goes on. So in the past 15 years, it was like the wind at our backs, and it was warming quicker, and maybe it'll be like facing the wind for the next few years. I wouldn't completely quote me on that.
No promises.
Does the calving glaciers in Greenland and I know there's not as much sea ice in the Arctic now and that stuff though, but that stuff coming down, I guess with climate change, with warming temperatures, that calving is going to increase, which will actually cool the Atlantic with all the ice coming down.
It's
Will that
actually
be enough to moderate the climate on land?
There's it's very complicated because it depends on where from Greenland the actual melting occurs. But I just, even last week, I saw an interesting presentation where they were showing that the increase of, let's say, melting from Greenland and on the west side of Greenland, going into the Baffin Bay up there, the bay between the two, it would cool the waters, and as a result, the ocean circulation might change a little bit there, and it actually might warm, so that it'd be like amplifying the warmth. There's definitely going to be impacts on that, and that is something that a lot of people are working on right now, because you do have all this cold fresh water going into the ocean that will be picked up by ocean circulation, and the impact that people have spoken about that hasn't been observed but maybe someday would happen would be that you would have the circulation slow down a little, and so you'd have less heat being pumped in, up into northern areas. But I mean, that's something that's kind of in the future. But that being said, I mean, the example I've seen is that Greenland has increased the amount of water it pumps into the Labrador Sea region by about 40% over the last 10 years, which is a lot. And as we saw, I said in 1972, the coldest year on record, that was caused by a bubble of cool water that went down to the Labrador Sea. So let's say if we had something like that happen again, it would be as if a year that was normal. It wouldn't be, there'd be no climate change that year at all. It would be colder than normal. Will that continually happen? I couldn't say. But it is expected that Greenland is going to lose a lot of ice. It's actually lost a tremendous amount. The projections that were being made by climate modelers say 10 years ago are obsolete for Greenland now by huge amounts. They were predicting maybe that where it is now, they were predicting for 40 years from now. It's the amount of ice being lost there is tremendous, and also troubling the West Antarctic ice sheet. That's another big mass of ice that is, let's say, losing ice at a very quick rate. That was not expected at all. They weren't predicting at all the next century for it to lose ice, and it's losing a lot of ice. So there's going to be a lot of unexpected consequences, and understanding that is kind of what it's all about.
Yeah, I think that's part of the problem with public perception too, is that you guys, you did 10 years ago, you made all the predictions, and you were off, so what should we believe in now?
Yeah, well, that's always, well, luckily I'm not a meteorologist. So
exactly. You don't have to deal with it on a daily basis.
Yes.
The talk and change in sea level.
Yeah.
Will the effects be comparable here to further south?
So sea level is really interesting. It doesn't happen evenly. So some areas experience more sea level rise than others, and that has actually to do with a number of factors, even including the Earth's gravity. So one of the interesting things about, say, Greenland, for instance, is they've got a couple satellites up there that are circling the Earth, and they're measuring at very high precision how much gravitational pull is coming from the Earth at different spots. And they're actually detecting that Greenland is pulling less on gravity because it's losing so much ice. It's losing the equivalent of 2 Mount Everests per year worth of ice. So if you take the whole mass of Mount Everest, and you times it by 2, that's how much ice is being lost from Greenland each year. Antarctica, it's almost 1 Mount Everest in its whole is being lost. So that's a lot of ice, and that means that the areas, the changing patterns with where sea level rise is coming from, means that there's different variations in what areas will be impacted the most. One thing that Labrador is in some ways fortunate, and some parts of Canadian Arctic are fortunate about, is that we were covered by ice during the last glaciation most recently. So when that ice disappeared, the surface underneath was, let's say, when that big heavy ice was pushing down on the surface, the land was depressed. And so when the ice melted away, the land in a lot of areas is still rebounding. So in some areas, sea level rise is declining, and some areas, the eastern Canadian Arctic, because basically the weight that was being held down by those ice sheets that have just disappeared is being released, and the land's rising faster than sea level is rising. Sea level rise is not expected to be an extreme issue for coastal Labrador, luckily. Not compared to
Newfoundland.
Not compared to some other areas. Certainly not compared to when you consider areas like India and some of those areas that have a lot of areas below sea level that are in areas that are expected to have a lot of sea level rise. Newfoundland does have some concerns in certain areas, but Labrador is, luckily, that's one of the issues that shouldn't be a major concern, but it's difficult to predict that kind of thing, right?
You mentioned adapting to the changing climate. I'm just wondering, from your perspective, are governments and industry doing enough, or are there things they should be doing?
Well, I would say that in Canada, over the past decade, there's been a bit of a change in the focus. So for a long time, there were a lot of people who were aiming at mitigation, so trying to get emissions down. And I think there's been a bit of shift in government policy towards adaptation. So there is funding available for certain projects. There's one called ADAPT, for instance, that do that type of work. That being said, to do proper adaptation, you have to have the core research to know how changes will occur, where it will occur, and that's where there's been a gap. So there has been availability of funding for adaptation, but one of the problems is if you're a group that wants to go and do some work in that regard, you've got to kind of fill the knowledge gap before you even start doing that type of work. And that's kind of a challenge. And it's, I think that there should be more of an effort going forward. And another problem with that is that monitoring is not something that there's a whole lot of funding for. There's a lot of funding for going out and getting results, but not for monitoring how these things go. So you have a project, most people, you say somebody does their PhD, they do their 4 or 5 years of work, and where is the continuation of funding for continuing some of those projects? That's where there's difficulty. So for me, for instance, I would love to set up a bunch of sites to be able to monitor continuously, but whether that's going to be possible or not, you need partners who are willing to kind of foot the bill. I do think that there is more of a push towards adaptation now, and I think part of that comes from the realization that in Canada in particular, and in northern Canada, there's going to be continued impacts, whether emissions stop altogether or not, because there's a certain degree of warming that will still occur, but it's a lot easier, I think, for Canadian government, for instance, to rationalize putting money towards adaptation. I think there should be more in some ways, but there also has to be more of the core research. I mean, when it comes to permafrost work, for instance, in Labrador, we're starting from scratch for the most part. And that's the big when you haul up a map and there's really nowhere on this map that 100% there's permafrost because there hasn't been previous work done in those areas, then it means you're starting right from the beginning and you're devoting a lot of resources towards that. I'm pretty lucky. My supervisor for my PhD, he's a big shot in permafrost, so I have his experience to lean on. And that's somewhere that I think collaboration is very useful. Let's say where if you're doing adaptation projects, it's very useful to bring in expertise. And I think that I've been pretty fortunate to have him kind of helping out, let's say.
All right, well, thanks, Robert.